Let's do one more problem with heat transfers. This one is actually exactly what we're going to do in the lab. We're going to take some pieces of metal. We'll get their mass by putting them on the electronic balance. This piece of metal has a mass of 28.2 grams. We're going to heat them in some boiling water. So eventually the temperature of the metal will be pretty close to the temperature of the boiling water, close to 100. In this case, 99.8 degrees. That hot piece of metal is placed in a coffee cup calorimeter containing 150 grams of water at 23.5 degrees. So here's kind of my setup. I've got some kind of a container of water. A coffee cup calorimeter is probably just a styrofoam cup. It's some kind of a container that is a good insulator. We use styrofoam in the lab because it's a better insulator than glass. So we're going to have cool water. Tap water is somewhere in the 20s. This tap water is at 23.5 degrees. So I'll just call this cool water. And then we add the hot piece of metal. All right. That hot piece of metal is placed in the calorimeter with the 150 grams of water. So I can kind of imagine then that the metal is going to cool as it's in the cold water, but the temperature of the water should increase as I add this hot piece of metal, so that the final temperature of the metal-water mixture is 25 degrees Celsius. So we're going to use these metal cylinders. We'll plunk that hot piece of metal in the cool water. So we'll call this hot metal. And energy is transferred from the hot metal to the cold water. So the temperature of the metal will cool. The metal will start at almost 100, but it'll cool down to 25 degrees. The temperature of the water increases. It goes from 23.5 up to 25 degrees. Calculate the specific heat of the metal, assuming no heat escapes to the surroundings or is transferred to the calorimeter. Which again, we're trying to use styrofoam because it's a good insulator. And hopefully then no heat loss. That will be a major source of air. We probably don't have a lid on this container, so heat can escape out the surface of the liquid, and it could cause a source of air, which again we'll kind of talk about when we run this one in the lab. Now with these heat transfer calculations, there's usually one particle that you know everything for, and you can calculate the delta H. So we know this is water, we know its temperature change, we know its mass. Let's start with the water. So we can do energy absorbed by the water. This is endothermic for the water. So I'm going to use my mass times temperature change times specific heat equation. I have 150 grams, which is really 150 milliliters. Whoopsie, I want to leave that in grams. Hello. Sometimes they'll give you milliliters, and for water, 1 milliliter is 1 gram. This one is in grams. We'll measure ours by volume in the lab, but then the volume of water you use is your mass. The density of water is 1. Temperature change is final minus initial. The final temperature of the mixture is 25 degrees Celsius. Initially it was 23.5 degrees Celsius. So the water temperature increases by about 1.5 degrees. And then in this temperature range, the water is definitely a liquid, 4.18 joules per gram degrees Celsius is my specific heat of water in the liquid phase. A constant, we just look it up. All right, so let's plug this in and see what we got. Delta H is positive, which is good, endothermic, by 940.5 joules. Okay, so this is energy absorbed by the water, endothermic for the water. But now, assuming no errors, all of that energy that was absorbed by the water came from the hot metal. So we can set up a very similar calculation, but in terms of the metal. And we're going to call this energy released by the metal. All right. But now that we calculated the delta H, we can use that in reference to the metal. These are going to be the same numerical value. The only difference is that if this is energy released, we're going to make it negative. My delta H is negative 940.5 joules. Assuming no errors, such as heat loss to the surroundings, which is an error that we'll have to look at in the lab, all of the energy absorbed by the water was released by the hot metal. So now we can just do everything in reference to the metal. This is beautiful. The mass of the metal is given to me in the problem. It is 28.2 grams. The temperature change of the metal is a little funky. The final temperature is 25 degrees. It tells me that the final temperature of the metal-water mixture is 25 degrees Celsius. So they both end at the same final temperature, but initially the metal was pretty warm, 99.8 degrees. So we have a negative temperature change. We have a negative 74.8 degree temperature change, and that's okay. It just means that the temperature of the metal went down. The metal started almost the same as the boiling water, and it cooled to the same temperature as the tap water. And then finally, specific heat will be my variable. So as long as I know the delta H, I could solve for any of these variables. Or maybe they would have told me the identity of the metal, and then I could look up the specific heat. And they could have said, what's the mass of the sample? We could solve for any variable as long as we know 3 of the 4. All right, let's plug this in. We are almost done. Specific heat of my metal is 0.446 joules per gram degrees Celsius. Now then, this would be a way of identifying an unknown metal. You could look this up on a chart and see which metal it matches most closely to. Which, if I kind of page back, this is probably kind of close to iron. I'm looking at the specific heat chart earlier in the study guide. It's got iron listed as 0.449. This is probably pretty darn close, huh? So with these energy transfer calculations, you almost have to think of it as 2 calculations. There's one substance where you can calculate delta H. You'll know the mass, you'll know the temperature change, and you'll be able to figure out the specific heat. Here we knew it was water in the liquid phase. Then you can use that energy for the second particle, but often we have to change the sign. The energy is always transferred from the warm object to the cool object. So for the metal, this is exothermic for the metal. Heat transfers, and it ends up giving us a positive specific heat because we'll get a negative temperature change. Often a negative delta H will mean a negative temperature change. If energy was released, the temperature probably dropped. This is essentially what we're going to do in the lab. It's great. So if this type of calculation starts to click with you, I think you'll enjoy this next lab.